Hello, everyone. I'm Hong from University of Waterloo. Today, I'm going to talk about a new approach to network design. It is widely recognized that linear programming is the most general and powerful approach in designing approximation algorithms for network design. Our new approach introduces ingredients and the techniques from spectral graph theory and the discrepancy theory. We show that the new elements can significantly extend the scope of network design. Today's talk is based on a joint work with my supervisor Laplacian. Let's start with some background about network design. Generally speaking, in network design problem, we are given an undirected graph G as input. Each edge has a cost. The goal is to find a minimal cost subgraph satisfying certain requirements. The most well-studied network design problem is the so-called survivable network design, where we have an additional input, a connectivity requirement FUV for each pair of vertices UNV. The goal is to find a minimal cost subgraph H so that there are at least FUV H disjoint paths for each pair of vertices UNV. This captures many classical problems as special case. For example, the minimum spanning tree problem, minimal standard tree problem, minimal k-edge connected subgraph problem. The classical approach for this problem is based on linear programming relaxation. Jane showed that there is a LP-based two approximation algorithm for survivable network design. The algorithm uses LP iterative rounding technique, which is based on a nice structural characterization of the LP polytope extreme points. This is still the best known algorithm for survivable network design so far. And the techniques of iterative rounding has been extended to many more general settings, for example, element connectivity, vertex connectivity, etc. Besides connectivity requirements, we may also want to incorporate more constraints into network design. For example, people have been studied the degree constraint, where there's a degree upper bound dv for each vertex v in the graph. And the iterative rounding techniques has been successfully extended to degree constrained network design. More generally, some linear packing and covering constraints have also been studied, but not much is known. In particular, when there's no underlying structure behind the constraints. It is also natural to consider the shortest path constraints, where unfortunately it is hard to approximate with the shortest path constraint. Then let's move on to consider the motivations of introducing the spectral approach and our new results. As there are many other natural network design requirements that don't fit into the traditional linear programming framework. For example, the graph expansion, effective resistance, fast cover time and missing time of random walks on the graph, or fast commute time between vertices in the graph. As we know from spectral graph theory, all these properties are related to graph spectrum. Therefore, it is natural that in a network designer want to have a better control over the algebraic properties of the graph in the context of network design. Let's consider some specific examples. The first example, algebraic connectivity, which is defined as the second smallest eigenvalue of the Laplacian matrix of a graph. Gauche and Boyd has considered such a problem where we want to find a subgraph with certain sets to maximize the algebraic connectivity. There was some progress towards this problem, but in general, the problem has not been settled. And in particular, the known results cannot handle the general edge cost. But why are we interested in maximizing algebraic connectivity? A lower bound on algebraic connectivity will implies fast missing of a random walk on the graph. It will also imply a lower bound on the graph expansion. All this actually imply the resulting graph is a well-expanding graph, which is a very useful property in many applications. Therefore, it's natural we want to incorporate the algebraic connectivity constraints into the network design. Our next example, let's consider effective resistance. Effective resistance can be treated as an interpolation between shortest path distance and the edge connectivity. In many applications, it could be a better measure of well connectedness than the shortest path distance and the edge connectivity. Gauche, Boyd, and Saberi studied this problem where we want to find a minimal cost stop graph with total effective resistance bounded. They gave many applications of this problem, but there's no known approximation algorithm. And together with our co-authors Chen, Sheard, and Wang, we also studied a problem where we have a single pair effective resistance constraint. However, in general, for all these problems, we don't know too much, especially for the approximation result. Ideally, we want to solve a generalized survivable network design problem, including all these constraints we have talked about. We can actually write a large convex program for this problem. This convex realization can be solved in polynomial time using the ellipsoid method. And after obtaining an optimal solution X for this convex program, then our goal becomes to design a rounding scheme to find a good integral solution. Then let's consider our progress towards this problem. Our first main result, we show that there is a polynomial time randomized algorithm that returns a 0-1 integral solution satisfying all the connectivity, effective resistance, algebraic connectivity constraints simultaneously with high probability. And the cost of the returned solution is not far away from the fractional optimal value. They are subject to some additive error terms, where here n is the number of vertices and the C max is the largest cost in the input. We remark that if the fractional value is at least n times C max, then this implies a constant approximation to the generalized survivable network design problem. And furthermore, the solution we returned will approximately satisfy the linear packing and the covering constraints with high probability. And we remark that our first result can now handle the degree constraints. Then let's consider a concrete example to show how we can apply the first theorem. Suppose in the survivable network design problem, the connectivity requirement FUV is greater than K for all pairs of UV. For example, we are in the K edge connected subgraph problem. Further, we assume all the edge costs are from 1 to big O of K. Then it follows that the fractional optimal value is at least n times C max. Then as we have discussed, our first result gives a constant approximation spectral algorithm to this problem. We remark that even in this simple restricted survivable network design setting, we don't know how to achieve constant approximation without using Jane's iterative rounding technique. And note that, importantly, we achieve this constant approximation where incorporating many other additional constraints, where each of these individual spectral constraints was hard to handle previously. Then let's talk about our second result, which is an integrated gap result. Given a fractional optimal solution X, Suppose X satisfies some additional assumptions, then we can show there exists a 0, 1 integer solution such that the solution approximately satisfies all the connectivity degree, effective resistance, algebraic connectivity constraints simultaneously. And the cost of the solution, integer solution, is at most 1 plus epsilon times the fractional optimal. So the advantage of this result is that we have a much stronger guarantee on the cost. We can get rid of the additive error term. And also we can deal with the degree constraints with this result. But there are several drawbacks of this result. The first one, we can only approximately satisfy the constraints. The second one, we cannot handle additional linear constraints. Third, this result is non-constructive. We can only bound the integrated gap. And finally, we have some additional restrictive assumptions on the fractional solution. But we have shown in our paper, there are still some interesting examples captured under these assumptions. Okay, then let's move on to talk about our spectral approach to achieve all these results. First, let's recall some properties of the Laplacian matrix. Given a fractional solution X, we define the Laplacian matrix of the fractional solution as the sum of XE times LE, the Laplacian matrix of HE. As observed in spectral specification, the quadratic form of Laplacian matrix with respect to the indicator vector of a set S is exactly equal to the fractional value of the cut S. Therefore, Laplacian matrix retains the information of all graph cuts. Because of this, we observe that the mathematical question underlying the rounding scheme of generalized survivable network design problem is the following spectral rounding problem, where we are given a fractional solution X and a non-negative cost vector C. We want to find the integral 0, 1 integral solution Z such that the Laplacian matrix of the integral solution is approximately equal to the fractional Laplacian matrix, and the cost of our integral solution is approximately equal to the fractional cost. If we can solve this spectral rounding problem, then we actually can satisfy many constraints. For example, if we can satisfy the spectral lower bound, then we can satisfy all the connectivity requirements. This follows by just considering the quadratic form of the Laplacian matrix with respect to the indicator vector of all cuts. Then we can also satisfy all the effective resistance constraints because it is well known that the effective resistance can be written as a quadratic form of a pseudo-inverse of the Laplacian matrix. Finally, we can also satisfy the algebraic connectivity. We can simply check the second smallest eigenvalue of the Laplacian matrix. We remark that if we set epsilon equals to 0 here, we can actually satisfy all the constraints exactly. And if we can satisfy the spectral upper bound, then we can also satisfy the degree constraints by simply tracking the diagonal entries of the Laplacian matrix. Therefore, our two main results about the generalized survivable network design are just simple consequence of the spectral rounding. And we remark that in many applications, it is algorithmically more convenient to control the algebraic properties in order to control the combinatorial properties. Then let's talk about some known results about spectral rounding. A result by Alan Zhu, Li, Singh, and Wang can be rephrased as a one-sided spectral rounding result. With an assumption on the sum of x's, they show that there is a polynomial time algorithm to return a 0-1 integral solution such that the spectral lower bound is approximately satisfied, and the number of edges we picked is at most the sum of x's. They use this result to achieve near optimal approximation algorithms for many experimental design problems. And this result actually can already solve the survivable network design problem with uniform edge cost. But the connection was not established before. And this result is crucially relying on a regret minimization framework developed for spectral specification. We generalized this result to handle general non-negative linear constraints. So we show that there is a randomized polyton algorithm to return a 0-1 integral solution such that the spectral lower bound is exactly satisfied with high probability. And furthermore, for any non-negative linear constraint, we can satisfy it approximately up to some additive error terms. And we remarked that our algorithm does not need to know the linear constraints in advance. And we can handle up to exponentially many of the non-negative linear constraints because the failure probability of each of them is exponentially small. We can also show that this upbound is best possible. We have some tight example. Our first main result for network design is just a simple consequence of this theorem. Then let's consider our algorithm. In our algorithm, we first normalize the input so that the fractional solution equals to identity. This is convenient because we only need to bound the minimum eigenvalue of the integral solution after this transformation. Then, in each iteration, we maintain a density matrix AT, which induces a potential function, giving higher priority to rows vectors, rows not well-covered directions. And then in each iteration, we also sample an edge with probability proportional to this term. Let's take a closer look at the sampling probability. If we just sample with respect to XE, then it is just independent rounding. This will preserve the cost with high probability, but will not satisfy the spectral lower bound. So we introduce this adjustment term. As we had seen before, like the definition of AT guarantees that we give higher priority to rows vectors VE pointing to the non-well-covered directions. So this adjustment can help us to improve the minimum eigenvalue. Then we return all the sampled edges after an appropriate chosen number of iterations. Then let's consider the analysis of the algorithm. In the algorithm, the choice of AT is very important. Our choice comes from the L-half regularizer for the regret minimization framework. If we choose AT in this form, then the regret minimization framework provides a way to lower bound the minimum eigenvalue of the integral solution. Then according to our sampling distribution, we can show that when the algorithm terminates, the expected spectral lower bound and the expected cost are all as desired. To guarantee we can achieve both of these simultaneously, we need some concentration. However, different iterations are not independent because the sampling probability is based on the density matrix AT, which is defined with respect to the current solution ZT. But fortunately, we can use some martingale-related inequalities to show concentration. Therefore, this can finish our analysis. Thus, the main idea here actually is quite simple. We have some quick remark about this algorithm. First, the algorithm I just present only returns a multi-set solution. We need some more involved calculations to recover 0, 1, 1 solution. And this algorithm can be treated as a randomized version of the greedy algorithm in Alanju and co-authors ICML paper. We also got some improved result over the conference version. The new result is available on arXiv now. Then let's move on to consider some known work about the two-sided spectral rounding. So a result from King, Lu, and Song shows that with some additional assumptions on the fractional solution X, we can show there exists an integral solution Z such that the two-sided spectral rounding is possible. Their result is based on a method of interlacing polynomials, so their result is non-constructive. And note that here, the assumptions on effective resistance corresponding to the short vector assumptions in MSS. So this is not the original statement of King, Lu, and Song's result, but it's just a direct consequence from their main theorem. We generalize their results by incorporating one additional linear constraint. We remark that we can only handle one more non-negative linear constraint. And the proof actually is quite simple. It's through a neat black box reduction from rank 2 case to rank 1 case studied by King, Lu, and Song. Okay, finally, let's summarize our talk. The main contribution of our work is to propose a spectral approach to design approximation algorithms for network design problems. And we showed that the techniques developed in spectral graph theory and the discrepancy theory can be used to significantly extend the scope of network design problem. We believe that this connection will bring new techniques and stronger results for network design. And we also believe it will introduce new formulations and interesting questions to spectral graph theory and discrepancy theory. Let's conclude with some open problems. The first one, can we fully recover Jane's iterative rounding results with spectral approach? The second one, can we get some refined spectral rounding results in spectral settings? For example, can we get better dependence in epsilon with only effective resistance constraints? Okay, that's all I want to talk about today. Thank you very much for watching.